All right. So I'm going to talk about a number of things, the relationship between the astronomy and the periodic table, starting with a brief history of the universe, which I just discovered was another talk that I gave here. And then how looking at atoms on the Earth tells us things about things that we see in our telescopes, spectroscopy and redshift in particular. And then where do the elements come from? How do the elements affect the life cycle of a star? So the basics are, until recently, everything we've ever learned about anything in the sky has come from dissecting starlight. Now we have new channels now, but radio astronomy didn't start until 1933. The latest new channels are neutrinos, looking at relic neutrinos from the Big Bang, which is really, really hard, and gravity waves, which has told us some amazing things. And we can probe the solar system with machines. I actually do a talk about asteroid mining, where I talk about the sample return missions from the different asteroids. So we can learn about the chemistry of things in our solar system, but we can't touch things outside the solar system. They're too far away. And the only thing that we can learn about those things comes from the light that falls on our eyeballs. And we had to learn how to interpret what that light tells us. So here's our brief history of the universe. There is a point right at the beginning. The little spot there is the hot Big Bang. And I refer to it as the hot Big Bang because some theories say there was a cold Big Bang just before the hot Big Bang. And then there was a very period of cooling off as the universe expanded until 380,000 years after the Big Bang. Positive and negative charged particles could recombine. The universe was cool enough that neutral atoms could be formed out of the plasma. And when that happened, the light escaped and went across the universe. And this is a picture taken by one of the cosmic microwave background telescopes, because that's what we see is from that period. That's as far back as we can see in optical light, is that period of 380,000 years. There was a dark ages when there were no stars. There was nothing to see then. And then star formation started. All the nucleosynthesis happened right in this very tiny realm here. And to divide it up by a log scale, we talk about the electroweak era, and look at the length of time. Significant eras in the universe were happening well within a tiny fraction of a second. 10 to the minus 10 seconds, we had the electroweak era, when electromagnetism and the weak force were combined because the energy in the universe was high enough that they were the same force effectively. And then nucleosynthesis basically ended about 3 minutes after the Big Bang. That was when we had the hydrogen, the helium, and a tiny little bit of the next couple of elements. So then this says 500,000 years, other people say 380,000 years, but that's when we had neutral atoms after that, and light could travel across the universe. And of course, one of the reasons this image has this curved profile, there was expansion, and then we thought the universe would slow as gravity slowed the expansion of the Big Bang, but in reality it's gotten faster. And we'll talk a little bit about how we know it's gotten faster. So there's these three major eras. The radiation era was up to 380,000 years after the Big Bang. The matter era, 380,000 years, up to 8.8 billion years after the Big Bang. And then something happened 8.8 billion years after the Big Bang, where a new something that we call dark energy took over and began to push the universe apart. Now this is still very controversial. There are some mathematical models of the structure of the universe that don't require dark energy. So it's still very early, and we don't have definite stuff about dark matter. Has good, solid physical evidence for its existence. We haven't been able to find dark matter particles yet, but a lot of the experiments I've been involved in are looking for dark matter particles. Dark energy is different. Dark energy has less of a footing, other than the fact that telescope measurements tell us the universe is expanding faster instead of slowing down. So how do we know anything about the first moments after the Big Bang? This is something that took me a while to appreciate. The spots in the middle of our colliders. It used to happen at Fermilab, and now it happens at the LHC at CERN. Those points where particles are collided against each other are the hottest points in the entire universe. They are recreating conditions that haven't existed since 10 to the minus 12 seconds after the Big Bang. At that time, the temperature of the universe was 10 to the 16th Celsius. We don't put names to numbers like that. They're just powers of 10. And the size of the universe at that time was about 10 million kilometers, which fits inside the orbit of Mercury. The entire universe fitting inside the orbit of Mercury, and the temperature that high. And that's what's going on in these collision points. Well, Fermilab didn't get quite as hot as CERN, but CERN is the record now for colliding particles together and creating temperature conditions that haven't existed since shortly after the Big Bang. And I believe it's true to say that that's true for anywhere in the universe. There are particles that come in through the atmosphere that have energies far higher than we know how to produce with accelerators on Earth. So and actually there are some particles that enter the atmosphere that nobody knows how they got so much energy. So maybe those collision points aren't the hottest places in the entire universe, but we don't know how some of the things that come to Earth get that energy. And actually that was one of the reasons almost every time CERN turns on, the LHC turns on, someone sues it because they say it's going to produce black holes that are going to eat the Earth. Okay? And the rationale, the physicists tell them, look, there are particles hitting the Earth every day at higher energies than we can produce on Earth. They're not producing black holes. The Earth is fine. So, but it's amazing to me that goes on all the time. But the key thing to remember about the early universe is that it was much simpler than it is today. And I'm serious, there was no chemistry. You can't have chemistry until you've got neutral atoms. And the behavior of these fundamental particles is really simple. So this is the LHC, and I've actually worked on a couple of different experiments at the LHC. We are proposing a new one specifically to look for dark matter, because if you look at these detectors, and by the way, if I say anything that somebody doesn't understand, I welcome questions and interruptions. It's absolutely fine. So these collision points where the proton beams collide against each other, there is a limit to how much of the energy of those collisions you can collect in these halls. And that limit actually comes from the size of the beam pipe in the middle of the experiment, because you can't put detectors inside the beam pipe that will block the beam. So one of our proposals is to build another tunnel that doesn't even connect to the LHC, which is called the Far Forward Facility, which can look in either direction, because these particles are coming out of both sides of the collider. And we would put a series of detectors in the Far Forward Facility, which are specifically looking for dark matter particles. We think there are things that you just can't see because of the structure of the detectors until you actually get outside and are tangent to the collision point. So that's what we're trying to propose, and of course it's a matter of waiting for enough money to get something like that. So in terms of what holds stuff together, this is a very informative table that gives you the relative strengths of things. And we're gonna talk about these things in more detail, but the strong force, which is given a relative strength of 1, that's the force that can hold protons to protons in the nucleus. There is a force which is mediated by a particle called a gluon, because it glues particles together. And you know, protons have the same energy, same electric charge. Objects with the same electric charge try and repel each other. So this force has to be stronger, and it's over 100 times stronger than the electromagnetic force, which is trying to push those particles apart. One of the big differences is the range of the strong force is very small. The strong force is not visible outside the nucleus. These gluons and things, we don't see them outside nuclei or far away from the particles in the nucleus. So electromagnetism, that's all of chemistry. The electrons that orbit around the nucleus, those are what interact to produce all of chemistry. The weak force is the force that's involved in radioactive decay. So there are heavy exchange bosons, and when I was a young mechanical engineer at Fermilab, we first discovered the W and Z bosons. I think CERN discovered one and Fermilab discovered the other. And then one of the anomalies of this table is gravity. And we really do not have a theory at this point that unifies gravity and all the other forces. And one of the things is the relative strength of gravity is so small, 10 to the minus 39 compared to 1. In most particle experiments, you can completely ignore the effect of gravity until you do ultra-cold neutron experiments. Ultra-cold neutrons are so close to absolute zero that they can literally bounce like ping pong balls. And their trajectories are affected by gravity as you move them down a beam pipe. Ultra-cold neutrons are completely amazing. So if you're looking for periodic tables, this is all you need. This is the periodic table of the fundamental particles, okay? All of the nuclei in the periodic table are made of these two quarks, up and down quarks. And the electron is the third particle that circles around the nucleus. And the periodic table is basically a counting game. You just keep adding to it and you get new things. Every time you add another proton, you get another element. And that element behaves differently because the electrons do different things in their energy shells around it. Nobody knows why there are 3 generations of quarks. Okay, also when I was a young mechanical engineer, we built experiments at Fermilab to look at the charm quark and the strange quark. Top and bottom are so heavy that they are only formed in the big collider experiments. None of these particles last very long, and no one knows why there are 3 generations of quarks, and we've never seen a 4th generation of quark. And because I'm just a bachelor's in physics. I'm not a PhD in physics. A PhD in physicist might be able to tell you whether or not the reason we haven't seen a 4th generation is we just haven't built a particle accelerator big enough. I don't know the answer to that. But nobody knows why there are multiple generations. Now these are the neutrinos. Boy, these are odd things. They were first discovered as products of radioactive decay because every time a nucleus would decay, it would give off a positively charged electron, a positron, or a negatively charged electron, or an alpha particle. But if you added up all of the energies, the energy of the original nucleus and the energy of the particles coming out, there was always a missing amount of energy. And they finally discovered neutrinos carrying away the missing amount of energy. We used to think neutrinos had no mass. We now think that they do have a mass and they don't travel exactly at the speed of light. They travel very close to the speed of light because every time they're produced, they're given enough energy for their mass that they're immediately traveling at close to the speed of light. The electron also has 2 heavier cousins, the muon and the tauon. And Fermilab is currently experimenting with muons right now. There are 2 experiments at Fermilab, the G-2 experiment that I was involved in, and the mu2e experiment I was also involved in. And I don't know who's doing anything with tauons, but these are also, this guy is about 200 times heavier than this guy. If you take the ratios of these energies in GeV compared to MeV, I mean, GeV is 1,000 times heavier than an MeV. So the generations, big mystery. We don't know why the universe creates them, why they're necessary. But the up and the down, that's how you make protons and neutrons. The ups and the down quarks have fractional charges, which we have never seen in nature. We've only seen integral charges, but in the early scattering experiments where you were bouncing particles off of nuclei, especially hydrogen targets where there's only protons in the hydrogen target, you can tell that there are multiple objects inside the proton. That's where quark theory comes from. The fact that when you bounce particles off of hydrogen or other heavier nuclei, it scatters in a way that is completely different than if the proton was a point-like charge. So the protons have positive 2/3, and to make a proton then, you need 2 positive 2/3 charges and 1 minus 1/3 from a down. So a proton is 2 ups and a down, and a neutron, you just have 1 up and 2 downs, and the electric charge is canceled. So you either have a positive charge of +1 here, or a 0 charge. And one of the things we'll see later on that's very interesting, neutrons also participate in the strong force. They have gluons, and it turns out they are absolutely essential to the heavier nuclei. So what is an atom? It's the smallest thing that you can cut and keep the chemical properties. If you cut the nucleus, now you've got 2 new elements. So they have different chemistries. And they're made from these 3 fundamental particles. And it took hundreds of years to figure this out. And one of the reasons is there are only 3 elements in the periodic table that you can find in their pure form on the surface of Earth. Gold, tin, and I believe the other one is lead. And, oh, copper. Copper is one. Probably not lead, because lead oxidizes. But those 3, you can, sure, but you can find float copper that's just a big block of copper. If you chip it away, it looks like copper. So those are really simple, and they're relatively easy to diagnose or figure out what's in them. But most things are rocks, right? Most things have really complex, not only complex collections of atoms, complex collections of molecules, which are groups of atoms, and then those molecules are grouped in complex structures. So that's why it took us hundreds of years to figure out what the periodic table was. And at the time, most chemists thought that the right way to organize the periodic table was by atomic mass. But there were a couple of places where you look at the chemical properties of the 2 particles, or 2 atoms rather, even though one is heavier than the other, and their chemistry is all wrong. And you flip them in the periodic table, and all of a sudden, the chemistry matches the column that they're in. We didn't figure out until 1911, Henry Moseley was the one who figured out the right way to organize the periodic table is with atomic number, the number of protons, which identifies what element it is. So here's a conceptual picture. This is a helium atom, 2 protons and 2 neutrons, surrounded by a cloud of electrons. And here's my first analogy for size. If you were to expand all of the atoms in a grapefruit up to the size of blueberries, the grapefruit would be the size of the Earth. Okay? So that's how much smaller atoms are with respect to blueberries and grapefruit than the Earth is. And the other one is, if you say that one atom is the size of a football stadium, the nucleus is just a mosquito in the center of the stadium. The electron shells are everybody in the stands. So nuclei look really small, and the atom is mostly empty space. Why I can't put my hand through this desk is because even though the atoms are mostly empty space, they're full of electric fields. So it's the repulsion between the electrons in the particles of this desk and my finger that are preventing one from passing through the other. There are also conditions in extreme compression conditions where you get things like the Pauli exclusion principle, where 2 objects they can't be close enough together unless their quantum numbers are flipped and things like that. So there's lots of reasons, even though this is mostly empty space and I'm mostly empty space, one doesn't pass through the other. So here's the periodic table that everybody's seen, right? We call it periodic because the chemistry of the elements in the columns is very similar. These guys, they're very reactive. They start fires. These guys are also reactive. Flush any of these guys down the toilet and the toilet explodes. okay, as people in college learned when they took sodium out of the chemistry lab and flushed it down the dorm toilet. Don't do that, young man. And you notice as you go horizontally, that's the numbers game. 3, 4, 5, 6, 7, 8, 9, 10. And life needs all of the elements in the first 3 rows and doesn't particularly need the elements in any of the other rows. And there's a reason for that. These elements that are lighter are also more abundant. And we'll look at the relative abundances in a bit. The universe, basically, life isn't old enough to have incorporated the heaviest elements in us in any significant way. So that's why we're made of hydrogen, carbon, nitrogen, oxygen. Phosphorus is another important one. But as you get further down the table, I mean, sure, there's iron in our blood. Oh, iron's in this row, right? So it's still within the 4 rows down in the periodic table. This is a table you might not have seen. It turns out, if you look at the atomic mass numbers, and this table doesn't have it, but so these numbers are what are called atomic numbers. They're basically just the number of protons in the nucleus. But a lot of periodic tables like this, especially if they're bigger, have numbers for the atomic mass. And the atomic mass is both the number of protons and the number of neutrons. And you look at a periodic table and a lot of those mass numbers are fractions. And you think, how can the atomic mass be fractional if you can't have a fraction of a neutron? The answer is there's more than one flavor of each one of these things. And if you plot the elements where the number of protons is on the x-axis, that means each vertical line is an element, and that means every box in a vertical line is a different flavor of the same element. They all behave chemically the same, but they all have different numbers of neutrons. And the different numbers of neutrons are they're incredibly important. One thing you notice, way down in the light part of the periodic table, these black boxes are the stable elements. You can have stable atoms that have the same number of neutrons and protons if it's light enough. But what happens as you get to heavier and heavier elements, the stable ones have more neutrons. The number of neutrons is on the y-axis, and the number of protons is on the x-axis, and the line of stability gets higher and higher above the equal number line. Okay, and the reason for that is that's the beauty of neutrons. Neutrons add the glue to the heavy nuclei without adding the repulsive force that the protons do. So the more neutrons you get in there, you can get stabler nuclei in the heavy elements by throwing more neutrons in with the protons. Now, the colors in this table indicate all of the boxes that aren't black represent an atom with a number of protons and neutrons called an isotope, which is not stable. So there are 3,339 nuclides, which are flavors of all the elements, but there's only 253 that have never been seen to decay. Okay, so most of these boxes represent elements that fall apart. They don't want to maintain their identity. They want to be something else. And this legend tells you how they decay. Do they give off positrons? Do they give off electrons? Do they give off alpha particles? Alpha particles are just helium nuclei, 2 protons and 2 neutrons. Some of them fission, which means they'll just crack and become 2 different elements. Some can throw off a neutron, some can throw off a proton. And when there's a white box in the table, like that one right there, there is no known element with that combination, no known isotope with that combination of protons and neutrons. You can try to make it in a particle accelerator, and it just doesn't happen. You don't measure it. So you zoom in on this table, and unfortunately, they switch the axes on this table. So now the protons are going up, and the neutrons are going on the x-axis. So the elements are actually in vertical columns. And what you see is that even the lightest elements have multiple, they're horizontal. They're horizontal. The number of protons is on the y-axis, so this is a carbon, 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 but increasing numbers of neutrons. So there are 6 boxes, 1, 2, 3, 4, 5, 6, 7 boxes for the hydrogen atom. We know about hydrogen, which just has a proton. We know about heavy hydrogen that we call deuterium. And we make tritium in our nuclear reactors and in a lot of our high energy physics experiments. These are really hard to make, and we don't even have names for them. They're just heavier versions of hydrogen, and they fall apart immediately. And every element has a line like that, where there are some, until you get to technetium, which has no stable elements. And actually, there are a lot of elements up here, up beyond the black, where there are no stable elements at all. They're all radioactive. So element number 6 is carbon. Look at how many isotopes of carbon there are. Just scads with different numbers of neutrons. Zoomed in even more, and you can see the line for hydrogen. And hydrogen is the simplest and most abundant atom in the universe. 1 proton, 1 electron. Deuterium has 1 neutron additional. Tritium has 2 neutrons additional. And then it keeps going to add up the other ones. And there are serious differences between them, even though their chemistry is exactly the same. If you make water out of deuterium oxide, heavy hydrogen, those ice cubes don't float in regular water. Regular ice cubes float in regular water, heavy ice cubes don't float. So there are visible macroscopic differences between elements that are different isotopes because the neutrons are weighing down the hydrogen atoms in the heavy water. There are significant differences between some of the isotopes, and this difference between helium-3 and helium-4 is incredibly important. The only way we have to get temperatures close to absolute zero is a device called a dilution refrigerator. And a dilution refrigerator mixes helium-3 and helium-4. Helium-4 is the stable version of helium. Helium-3 is also radioactively stable, but is lighter. It only has 1 neutron instead of 2 neutrons. It's also incredibly expensive. People who are talking about deuterium, tritium, helium-3 is expensive. Tritium is even more expensive. So people who are talking about building fusion reactors that burn deuterium, which is heavy hydrogen, and tritium, which is double heavy hydrogen, have to make the tritium because there isn't enough tritium in the world to run their nuclear fusion reactor on. And they could never afford it to buy it on the market. So that's why fusion reactors always talk about we're gonna take the neutrons that come out of the fusion reaction and make more tritium with them. So some of the differences between isotopes give us incredible things. The difference between helium-3 and helium-4 gives us the ability to make a refrigerator that goes down almost to absolute zero. So, and we just have to understand what are the differences. Then it all comes down to numbers. It turns out that these things have totally different superfluid transitions when you're trying to make them superfluids where it loses all viscosity. One, because it has an odd number of spin 1/2 particles, is a fermion, the other is a boson. And it turns out one of the reasons that the dilution refrigerator works is that at low temperatures, helium-3 atoms can ignore helium-4 atoms. They look like what's called a heavy vacuum to the helium-3 atoms. And the way the dilution refrigerator works is the helium-3 atoms boil out of the helium-4 mixture and cool off the final pot at the bottom of the dilution refrigerator, which achieves the lowest temperature. So it's really amazing stuff. I worked for 20 years for an experiment called neutron EDM that operated at, the dilution refrigerator could get down to 275 millikelvin. and the experiment operated at 400 millikelvin. So now we talk about electron shells, okay? And we look at these funny shapes that are associated with the orbitals around the atom. Those come from quantum mechanics calculations. This is a scan of a table I got, a really handy sheet that used to be available at American Science and Surplus, and I don't know if it still is. But it shows how when you start with the lightest elements and you start adding protons, it shows what the next element is, and it shows the number of electrons that are associated with that element, and how the energy orbitals fill. And after the between 3 and 4, you start to get mixing, where the 3d orbital has a slightly higher energy than the 4s orbital. And that explains that section of the periodic table that we always break out at the bottom, the lanthanides and the actinides. They all look chemically the same because this is the lanthanides, this is the actinides. The number of electrons in their outer shell is the same. The outer shell electrons are the only ones that interact with other atoms. So these elements are all difficult to separate because chemically they behave the same. And how to think about the conceptual breakthrough of quantum mechanics was that atoms are not like solar systems. In solar systems, a planet can orbit at any radius from the sun. But in an atom, electrons can only orbit in certain orbits, and they can't exist in between the orbit layers. And that's because electrons act like waves. And the electrons around the nucleus are standing waves. And standing waves come in discrete harmonics and don't exist they're not standing waves in between these harmonics. So that's where these energy shells come from, the fact that electrons can only exist at certain energies around the atom. Well, this is where spectroscopy comes from. When an electron makes a transition, from one energy level to another, it's associated with a photon. Well, a photon is a particle of light. So the wavelength of that photon tells you the energy or the color. If it's around 500 nanometers, it's green light. And the blues are shorter wavelengths and the reds are longer wavelengths. And these two different spectrums, when you see a black background and individual lines, that's an emission spectrum. That's a hot gas giving off certain colors. Like sodium arc lamps give off the double yellow line. That's a hot gas giving off these emission lines. When you see a rainbow background with black lines in it, that means that a hot gas was giving off light in front of a cold gas. And the cold gas was absorbing the emission from the other gas and producing these black lines. So that's why we talk about an absorption spectrum and emission spectrum. In one case, you just have the lines coming from the element, and in the other, there's a black body radiation that's all the colors, but some are being absorbed. So how does the Doppler shift work? If you look at a hot mixture of electrons that are giving off light of all different colors, you wouldn't see a redshift because it would just be a rainbow and you couldn't tell what was going on in the rainbow. The elements give us the ability to have fingerprints in the light. And in particular, we use the fingerprints from hydrogen, the Balmer and the Passion and the Alpha series, to see what is going on in the light. If you didn't have the fingerprints from the hydrogen atom, you wouldn't know where you were, and you wouldn't know that anything was shifting. So for example, if you look in the laboratory reference and you just heat up some hydrogen and you get this absorption spectrum that has these lines in this pattern, and the pattern is what tells you everything. The pattern for every element is different. And most of the atoms in the universe are hydrogen, which is why we use the hydrogen lines. If you're looking at a star and the star is moving away from you, you get this Doppler effect where if the star is moving away from you, the wavelength of the light it's emitting is spreading out, then its lines from hydrogen are shifted towards the red. That's why we call it a red shift. It's the idea that if you're behind the police car and the police car goes by, the pitch of the siren of the police car is lower because the waves are spreading out. In front, it's blue shifted. So if things are coming towards you, it's blue shifted. If things are going away from you, it's red shifted. Very few things in the universe are coming towards us. One of the things that's coming towards us is the Andromeda Galaxy. So the Andromeda Galaxy is actually heading towards the Milky Way galaxy, but all of the distant galaxies are moving away from us. And what you see is they move away by more and more. The pattern is shifted. So when you start seeing lines that look like this, and you have to know the differences between the wavelength lines, and you see them shifted over and over, now you can say something about how far away that galaxy is because of the expansion of the galaxy, and we'll talk more about that. But the point is that the elements provide the fingerprint. Without the pattern of lines that come from the elements, you wouldn't have any information coming in from the light. You just have a bunch of rainbows, which wouldn't tell you anything. You have to have this structure to be able to see how the structure changes depending on the motion of the objects around you. So the redshift so far implies objects moving at different speeds. And there is two actual components of that motion. Because near us, the redshifts aren't that great. They're small percentages of the speed of light. But as you get closer and closer to the edge of the universe, you can end up with redshifts that are larger, they're faster than the speed of light. That does not mean that those galaxies on the edge of the universe are actually traveling faster than the speed of light. What it means is the space between us has expanded so much since the light from those distant galaxies was given off that the light stretches. As light moves through stretched space, the light stretches. That's what the redshift comes from. So individual galaxies, they're moving through space at relatively slow speeds, 1% of the speed of light. But the expansion of the space between galaxies is not limited to the speed of light. Space can expand as fast as it wants to. And that's described in general relativity. And light that passes through expanding space-time gets redshifted. So this was a telescope that I helped build at Apache Point Observatory in New Mexico. It is the 2.5 meter Sloan Digital Sky Survey telescope, which was the first telescope that the Sloan Survey built. And we attached this $4 million CCD camera to the bottom of that telescope. And my job was to come up with the latches, the pneumatically powered clamps that hold that camera on the bottom of the telescope and also hold the spectroscope to the bottom of the telescope. They were two instruments that they switched off. And the latches could never fail, or the camera would fall and the thing would be over. But that never happened. So I'm very glad that the latches never had a problem. We tested them in the freezer at Fermilab to make sure they would survive in the cold on the mountain. And they worked. Those are the pneumatic latches. I went to Apache Point Observatory and assembled those myself. That is me, much younger and much thinner. And I loved spending time at Apache Point Observatory. It's where I learned to fear cows, because the cows in New Mexico have enormous horns. So I call it the old Sloan Digital Telescope process because they have expanded, they've upgraded the experiment a number of times. And they don't do exactly what I'm going to show you, but they did this 20 years ago. So they would look through the telescope, they would scan across the sky, and they would record images with the optical CCD, and then the astronomers would say, I want spectroscopy from these objects at these points. So they took a steel plate and they drilled holes in it at the location of those objects where the stars would be. And they connected the spectroscope to the back of the telescope, and they had to plug. The reason it was called a plug plate is you plugged a fiber optic cable into each one of the holes, and there were hundreds of holes, and ultimately they ended up with hundreds, if not thousands, of plug plates, which each one of those holes let the light of a single galaxy into the spectroscope, so they could individually measure redshifts on different objects in the sky at the same time. The Adler Planetarium used to have a map of the 3D map of the universe with the dark matter. That's what the Sloan Digital Sky Survey did. It created the first detailed map of the dark matter in the universe. And ultimately, I mean, I do another talk about the Sloan Digital Sky Survey. They added more telescopes. There's one in the southern hemisphere to see the rest of the sky. They have continued to work since 1999, if I'm not mistaken, when first light happened in the first telescope. They've continued to take data. All of the data is available online at sdss.org. It's all free. You can look at any image of the sky at any time of the year when they had that image. It's amazing. It's completely amazing. So now, where do the atoms come from? It used to be taught that there were only these mechanisms. Big Bang nucleosynthesis, where most of the hydrogen and helium came from. Stellar nucleosynthesis, fusion causes small atoms to clump together to form larger nuclei, bigger atoms. Explosive nucleosynthesis, we'll talk about the evolution of a star, but when you get up to iron, things stop working well in the star, because as you fuse iron, it doesn't give off energy, it takes energy. It's an endothermic reaction. And then cosmic ray spallation is another method of producing elements where cosmic rays break up carbon, nitrogen, and oxygen and increase. These elements, beryllium, boron, and lithium, are not well produced in stars at all. So you have to rely on this process. And these materials, they're wonderful materials. I'm glad that the universe is old enough to have made enough of them, because they're really useful materials. So this is a periodic table, an older style periodic table, that shows where we thought these elements came from. But it doesn't. We thought that all of these elements in the platinum group were made in supernovae, and it turns out they're not. These elements have so many neutrons in them, there aren't enough neutrons available in a supernova explosion for that to happen. But there are more than enough neutrons available when two neutron stars collide. And when the neutron stars collide and chunks of material come off of them, it evaporates into the heavier elements like gold and platinum and iridium. So this periodic table shows you exploding massive stars, that color, exploding white dwarfs. But merging neutron stars are this yellow color that explains a lot of these heavier elements. And we see this process in the gravitational wave telescopes that we have. So LIGO and Virgo saw a signal of two neutron stars colliding. And this was on August 17, 2017. They saw this signal. These two neutron stars produced 10 Earths worth of gold in one collision. So you get a lot of the heavier elements that way. Calculations that attempted to figure out how many elements, what percentage of elements formed during the nucleosynthesis period, the 3 minutes of the Big Bang, had a difficult time calculating the amount of lithium. It was a mystery for a very long period of time, until some Chinese physicists changed the parameters in the model, changed the way the early universe was modeled so that it was less ideal. If you model it as an ideal gas, you end up with problems with the production of lithium, but they changed it so that it was less ideal, and all of a sudden the right amount of lithium comes out of the simulation. So what is the connection between stars and elements? Basically, a star lights its nuclear fusion fire when gas in a nebula, which is mostly hydrogen, clumps together because of gravity. So gravity on the large scale brings mass together, especially in the early history of the universe. It was the distribution of the dark matter that produced the gravity that brought the matter together to produce the galaxies, because what we see is there's a large-scale structure to the universe. But that's another whole discussion about why the dark matter brought the galaxies along these long chains and bubbles. But a star burns its hydrogen through its life. And these are two chains of events that can happen. So this is the dominant process in our sun called the PP chain, where two protons collide, they form deuterium, they give off a positron and an electron neutrino. And in another one, two protons and an electron collide and create deuterium and an electron neutrino. And these then can go and continue fusing. And so you see these numbers here, 99.6% of the reactions that happen are this reaction here. And then these other numbers, of this reaction, 99.87 of them go this way, 0.13% go this way. And you can add up the total amount of energy that's released in each one of these reactions to get the total amount of energy coming out of the fusion from the sun. Now, another process that is less dominant in our sun is the carbon-nitrogen-oxygen cycle, where you get carbon atoms and protons forming nitrogen and gamma rays, or a nitrogen forming carbon-13, a positron and an electron neutrino, and so on, building heavier and heavier elements, and in some cases breaking those elements down again to be recycled back into the process up here. When you make the oxygen and other things that come back, here, the carbon that's produced over here comes back into that part of the cycle. This is also something that was described in a paper by the Sloan Digital Sky Survey, if I'm not mistaken. No, this is from Borexino. So Borexino was another experiment, one that I was not personally involved in. So this plot is a plot of the abundances, and it is normalized so that silicon is at exactly 1 million. So you say that I have 1 million atoms of silicon. What is the abundance of everything else? And this is a log plot, okay? So the hydrogen is way up here at 10 to the 4 orders of magnitude more than the silicon, which is if there'd be 1 million atoms of the silicon. And what you see is these are the ones that we were just talking about, lithium, beryllium, and boron, that are not well produced in the universe. So their abundances are suppressed compared to the carbon, nitrogen, oxygen. And then as you get heavier and heavier and heavier down here at the heavy end of the periodic table down to uranium, the abundance of uranium is absolutely tiny. And what you see is that 90% of all atoms in the universe are hydrogen, making up 74% of all the mass. Helium is 25%. Every heavier element than those two elements falls in the 1% of the mass of the universe that's left over in the normal matter. So, how many of you are science fiction buffs? Read a lot of science fiction. Have you noticed there's a number of science fiction stories, especially ones by Alistair Reynolds, that talk about the intelligent species of the universe competing over the heavy elements? That is a common science fiction trope about what would be a reason why alien races might not always get along, because there are far fewer of these very useful heavy elements, and it becomes a competition to see who gets them. So that's what the three-body problem was like that. There's a whole bunch of Alistair Reynolds stories that are like that basically involve competition over the very fewest number of atoms in the universe. So as a star ages, what it fuses changes. Its hydrogen gets used up and turned into helium, and when that happens, the star collapses for a bit until it gets hot enough to burn the helium. So stars change size and luminosity as a function of what they're burning. And you get these transition elements. These guys are transitory steps that get broken down and turned into other things. And then astronomers are funny. They talk about solar metallicity. In the periodic table, there's a clear group of elements that are called metals. But from an astronomer's point of view, because everything after helium is so low in abundance, everything is a metal. That's what they call solar metallicity. Every element heavier than helium is referred to as a metal. And there are inconsistencies between the measurements of abundances of the heavier elements in the sun that you measure directly and the models of fusion in the sun. So we have things to work out there. And a lot of the experiments that I'm working on have to do with neutrinos and understanding the properties of neutrinos, because it turns out if you look at a fusion reaction that gives off gamma rays are photons. So they're subject to what happens to the electromagnetic force. And the center of the sun is crowded with charged particles. So gamma rays that are given off in fusion reactions in the middle of a star can't make it out of the core of that star. They're constantly scattering off of other things around them. There's only one particle in the very early short periodic table that I showed you that can make it out of a stellar core, and that's a neutrino. So it turns out that the volume of a stars are actually inflated by the radiation pressure of neutrinos. So we might say, well, who ordered those neutrinos? Turns out they're very important in the life of a star. They determine how big the star is, and the number of neutrinos coming out is coming from what's actually being burned and how many neutrinos are being produced. So over time, and this is not to scale, as a star fuses elements and makes the heavier and heavier elements, they begin to fall into the center of the star. And eventually, in a process that we don't fully understand yet, a star collapses and then rebounds. And the rebound can be the total destruction of the star, which we refer to as a supernova, which can outshine an entire galaxy for a couple of days, or it can be a kilonova. It can be just a smaller rebound that blows off some of the shells of the star. I just found these pictures a while ago to show relative sizes, because we know that our sun is much larger than any of the planets. So you look at even Jupiter. Jupiter's tiny compared to our sun, and we know that Jupiter is way larger than the Earth. The Earth is this little tiny grain of sand over here. But our star is not a large star compared to other stars. Some of the brighter stars in the sky, Sirius, Pollux, Arcturus, they are much larger than our sun. And some stars are way larger than those. Those are red giants. People are thinking that Betelgeuse, or Betelgeuse, is near the point where it needs to explode. Whether it happens in our lifetime is really the question. But that's a star that's very close to the end of its life. And so here's the typical life cycle of a typical star heavier than our sun, because our sun never makes it to this stage. But it starts as a nebula of gas, collapses into a star, burns up the hydrogen until it becomes much larger as a red giant. It's bigger, but it's not giving off as much energy, and eventually it burns up what little fuel it's got, becomes a red dwarf, it can shrink down to a white dwarf. It'll heat up again as it begins to have enough energy to heat up to fuse the heavier elements, and that's what makes it go from red to white again. And then it can either be kilonova or supernova, depending on the mass of the star. A star has to be at least 1.4 times heavier than our sun to get to be a black hole. And basically what happens in a black hole is the star is heavy enough that when the core collapses, it collapses so hard that it forms a singularity that has an event horizon around it, where if you were a particle that passes through that event horizon, you would have to travel faster than the speed of light to get out of that event horizon. So that's why we call black holes black. Anything that falls into them is gone from our universe forever. Okay? But if our sun were to turn into a black hole at the center of our solar system, the only thing that we would notice necessarily is it would be cold. Okay? It's not that we would get sucked into a black hole. The orbital dynamics of the solar system would stay the same as long as the mass of our sun was there in the center, because the sun has 98% of all the mass in the solar system. Okay? We wouldn't see a big difference to the orbital dynamics of the solar system if the sun were a black hole. Mercury would, because the space-time around the black hole would get very strange, and Mercury might get dragged. What was that?
For 9 minutes, we'll be okay.
Well, yeah, after that, things would get really cold. Yeah. I'm just saying the gravitational structure out here from the sun would stay the same, because it's all measured from the center anyway. So here's what happens to stars that are a few times heavier than the sun. And the cool thing here, here's the host galaxy, here's the helium flash, and the supernova, which outshines the entire galaxy, which is just amazing to me, because there are hundreds of billions of stars in a galaxy, and one of them can outshine all the others. And these are the kinds of shells that you get, and these shells are full of the heavier elements that then get spread throughout the universe and turn into us. Okay? We come from the fact that many, many generations of stars created the heavier elements from the early hydrogen and helium and made the stuff that we're made out of. So how do we know the universe is expanding? This is another element of using sunlight or starlight to understand something about the universe. Edwin Hubble, back in 1929, was able to see, by looking at the spectroscopy of galaxies in his local neighborhood, that every one he looked at was redshifted. They were all moving away, and he was able to calculate how much faster does a galaxy at a particular distance away from us move than the next one out, or the next one out. So he came up with the Hubble velocity. And I'm not going to get into the fact that it looks like by different measurements there are two Hubble velocities. But what's more significant, knowing what we know now about the expansion, one of the things that Hubble missed is that since he was only dealing with a small population of galaxies relatively close to us, he missed the fact that there are areas of volumes of the universe that are not expanding at the same rate as others. And that's what, so this is his line where he calculated the Hubble constant of how fast galaxies were receding away. But the expansion of the universe is accelerating comes from two different experiments that were done measuring type 1a supernovas. And some of this data was collected in the Sloan Digital Sky Survey. But the supernova that they were using, the type 1a, was considered a standard candle. So no matter how far away it was the same brightness as another type 1a supernova. And I don't know how type 1a is defined, but they used that information to figure out that there are galaxies that, this is a very difficult graph to understand, but it has to do with galaxies that are dimmer than they should be because the universe expanded more than is expected. So there's this model here, the empty model, and these are all dimmer galaxies because they're further away. And the only reason they're further away is because space expanded more than we expected. So I haven't read these papers, and this is a tricky one to understand. There was a lot of controversy over this because some people thought that it was gas and dust that were affecting this measurement, and that was eventually resolved. But the main takeaway is the universe is not expanding uniformly, and parts of it are expanding faster than others. And so one of the things that astronomers have to deal with is that they often have clusters of lines that they call the Balmer forest or something like that, where the lines from hydrogen that they expect at a certain wavelength, there's a whole bunch of them near each other because they pass through different portions of space that were expanded different amounts. So, like with everything in science, there's always caveats. People are now saying that there are multiple ways to produce type 1a supernovae, and so that might take away its specialness as a standard candle for measuring distance across the universe. I don't know how this argument is going at the moment. I haven't been paying attention, but it can change the view of dark energy, because if the measurement that you made thinking you had a standard candle wasn't actually a standard candle, now your measurement is wrong. And there are reasons to believe that dark energy is on a lot less solid footing than dark matter. Dark matter is on really solid footing. And then there are some new cosmological models that predict the expansion without invoking dark energy at all. So what do we know? We have an amazingly accurate model of 4.6% of the mass of the universe. Okay, the stuff that we're made of, the stuff that's cold enough to have complex chemistry, that's us. And quantum electrodynamics, QED, fully relativistic theory of matter and electromagnetism that has been tested to 14 decimal places of accuracy, works incredibly well. And the whole model is called the standard model, but we also know the standard model is incomplete because it doesn't incorporate gravity. We don't know what dark matter is or if dark energy is. So, you know, we know a lot about our little local environment right here and how matter behaves and how we can exploit the properties of matter where we are right now. But there is an awful lot of universe out there that behaves completely differently, different energy scales that we don't know enough about. So atoms, 4.6%, dark matter, 24%. And the reason this pie is skewed is because to calculate the amount of energy that it takes to make the entire universe expand faster is an enormous amount of energy. That's why it looks like the bulk of the energy in the universe is in the dark energy. Because if there really is a force of nature that is able to push the universe apart, it's a strong one. So this is how I'm going to end. You're a ghost driving a meat-coated skeleton made from stardust. What do you have to be scared of? And that's all I have.